Good afternoon and welcome to today's webinar, Improving AI and Advanced Analytics with Outlier Detection, with your presenter, Warren Baird, Cloud Product Manager for Maya HTT. My name is Maria Ma, the Marketing Campaign Coordinator for Engineering.com, and I'll be your moderator today. First, a few housekeeping items to cover. Today's webinar will be recorded, then available for on-demand replay on Engineering.com. For attending this full live session, you'll receive a PDH certificate within 48 hours. If you have any questions, please submit directly in this webinar interface and we'll try to address all questions during Q&A. Now, without further ado, I'll pass it over to our presenter. Warren, over to you.
Thanks, Maria. Hi, as Maria said, I'm Warren Baird, a Cloud Product Manager at MyHTT. I wanted to start out by giving you a quick understanding of who MyHTT is, so you can understand where we're coming from for the rest of the presentation. So we started out over 30 years ago doing thermal simulation for spacecraft. So we created products to do numerical simulation for heat transfer. We've since branched out into many other fields. So we now develop a wide range of simulation products, products for data center management, and more recently IoT and AI. And we provide consulting services in all of these areas as well. We work very closely with Siemens in a wide variety of areas, and they actually resell many of our simulation packages. Overall, we've got a huge focus on engineering and industrial applications. Most of our employees are scientists and engineers, so we're very much focused in these kinds of areas. To give you a rough idea of some of the areas that we work in, we do design services, so we help people design software. We do simulation services, so if companies don't have simulation engineers in-house, we can help them perform the simulations themselves. We've got a lot of experience in manufacturing and CAM-related software. Of course, what we're talking about today, industrial Internet of Things and applied artificial intelligence. We also do a lot of custom software development, so building custom applications for people, either standalone applications or applications embedded in other systems. We also do a lot of automation and optimization, usually focused around CAD and engineering applications, and also product lifecycle management work as well. So we cover a pretty wide range of areas and can help with all kinds of things. And so I guess all this to say, I look forward to sharing some of this information with you today. So we're going to get started actually with a poll to get a better understanding of where some of you are with AI.
Attendees, please let us know which option below best describes your company's level of maturity around industrial IoT and industrial AI. Are you interested in the benefits of industrial IoT and AI? Or you're already collecting IoT data and looking to gain more benefit from it with AI? Or you've started proof of concept AI projects on IoT data? Or you're actively using AI to gain insight into IoT data? We'll give you a few more seconds to submit. Awesome. Thank you, attendees. Looks like we have a very clear winner here at 68% are interested in the benefits of industrial IoT and AI, and a tie with 30% each collecting IoT data to gain more benefit from it and actively using AI to gain insight into IoT data. Thank you. Warren, back to you.
Okay, thanks, Maria. Well, it's actually interesting. It's not too surprising. It actually matches a lot of what I've heard, although actually having as many as 13% actively using AI is actually pretty good. Most of the people that I've talked to are more in the earlier phases of that process, either interested in the benefits or starting to collect data and work with it. but not actively working with it yet. So that's it's good that we're seeing some people out there actively using it. So to get started, I wanted to talk a little bit about what outliers are and why should you care about them. Broadly speaking, outliers are data points outside the normal range in your data, as the name implies. But the interesting thing about them is that they do have a tendency to help you find interesting things in your data. A lot of the things that show up as outliers are going to be things that can lead to process improvements, that can lead to product improvements if you're creating products. They can lead to predictive maintenance, so predicting when you may need to perform maintenance tasks on various things. Now, at a high level, the kinds of outlier detection that people do generally break down into two different broad categories. There's low dimensional or univariate outliers, which involve looking at single time series. So, or maybe a few time series together, looking for changes in a small number of attributes effectively. And then what's called high dimensional or multivariate outlier analysis, where you're looking at a large number of attributes simultaneously, trying to find things that can find outliers, find interesting things in the data. I'm going to talk a little bit more about each of those in the upcoming slides. But first, I wanted to talk about some of the kinds of things that we're hearing about from our customers in terms of why they're looking at doing these kinds of operations. And you'll see a lot of different things, but it's common to see, for instance, someone who has a factory with thousands of IoT sensors, and they want to get some useful information out of that. They might want to see, okay, well, what particular combinations of values lead to quality problems, or what lead to potentially downtime, or what lead to particularly good quality. You might have people who are dealing with pumps who have instrumented the pumps and are trying to figure out how they can predict bearing failures, or how they can predict other kinds of failures, or when they need to perform certain types of maintenance on the pump. As I mentioned before, we work with data center companies, and so CRAC is an acronym in the data center space for computer room air conditioning. So we've talked with customers that have hundreds of different CRAC units, and they have all of them instrumented, and they want to be able to kind of compare the results and figure out what leads to some CRAC units being more efficient than others, and what they can do to kind of improve the efficiency. So there's a lot of real world problems that people are trying to look at, involve lots of data. And generally, if you have more than 5, maybe 10 variables, you're going to need the high dimensional or multivariate analysis that I was talking about before. So when you start to look into outliers, you'll see people talk about both outliers and anomalies, and some people use the term interchangeably. We tend to use them to differentiate them a little bit. The approach that we tend to take is that we look at outliers as basically any data points that are outside of the norm, that are outside of your usual area in your data set. Whereas we look at anomalies as something you can actually take action on. So you have your full set of outliers, and only some of them actually would be considered anomalies. So ones that are actually things that you can, fundamentally things that you can actually do something about. So really, we generally see the outliers breaking down at a high level into 4 different categories. So the first is we talk about data or semantic errors. So these are problems with the underlying data of some form. Some may be fairly low-level semantic or data problems. It might be a failed calculation. It might be maybe there's a maintenance period where the sensors were left on and you're collecting data that isn't good. It might be bad sensors or sensor connections shorting out, that kind of thing. So they'll definitely show up as anomalies. You may want to take action on them. If it's a bad sensor, you might want to replace the sensor. But it's not really the actual outliers aren't going to give you any more insight into what's going on in your factory or in your pump or your CRAC unit or whatever domain that you're looking at. The next category we call unusual and uncontrollable events. So these are things that are random happenings. but ones that aren't particularly informative, aren't particularly predictable. They aren't something that isn't going to happen on a regular basis. And I mean, an example there might be, you could imagine if you were looking at data for airplanes, you might have a particularly high headwind that's much higher than usual, and so the plane's engines have to run harder than usual, and as a result, the fuel efficiency is lower than usual, and that altogether might well show up as an outlier. But it's not really something you can do anything about. You know, sometimes you're just going to have really strong gusts of winds, and they're going to result in outliers. So they aren't really something that you can do to, there's not really any actions you can take based on that. So that would be an outlier, but not something that we would consider an anomaly as such. Now, when you get to the actual outliers, there's really a couple of categories here that we look at. There is advantageous anomalies. Now, a lot of people seem to think, or tend to think of the word anomaly as implying something bad, and that isn't always the case. You could easily have a situation where an anomaly is that your machine is exceptionally efficient, or the product you're producing is particularly high quality. So for instance, I don't know, maybe you're making batteries, and sometimes you end up with batteries where the capacity of the battery is much higher than usual. So that would be an anomaly, but it's a good anomaly. It's something that you actually want to repeat. So you want to be able to identify kind of what factors contributed to it, and then try to make those factors happen again as much as possible. And then the final category is what a lot of people tend to think of when they think anomalies, which are the disadvantageous anomalies. So these are the bad things. These are, you know, being able to predict a bearing failure, like we talked about before, or a pump shutting down, or, you know, any of the hundreds or possibly thousands of bad things that could happen in an industrial situation, and you know, identify what causes it, and then ideally put processes in place to avoid it, and or put in ways to recognize it in the future early enough that you can take action to avoid that in the future. Okay, and with that, we're going to move to our second poll.
Thanks, Warren. Attendees, what are your top of mind, highest value use cases for IoT data and industrial AI? You can select more than one of the options below. Find machine downtime root causes and run just-on-time maintenance, or reduce product quality issues, or increase first-time yield success rate, or increase energy efficiency, and or open up new business models, for example, power as a service or monitoring as a service, etc. We'll give you a few more seconds to submit. Thank you, attendees. Looks like our most popular at 63% is machine downtime root causes and run just-on-time maintenance, with second most popular at 57%, reduce product quality issues. Thanks so much for participating. Warren, back to you.
Thanks, Maria. Yeah, that isn't too surprising. Those are kind of the two top things that we tend to see, and we actually are seeing. Yeah, the third was the opening up new business models. That's something that we've been hearing a lot about lately. People who want to figure out ways to turn a product into a subscription. So you can, if you offer monitoring as a service, for instance, you can, instead of just selling a valve or something, you can actually sell a valve plus a subscription monitoring service to monitor the performance of the thing. And now all of a sudden you've got recurring revenue, which is pretty big for a lot of companies. So yeah, those are interesting results there. Okay, so I want to talk a little bit next about data cleaning, because I mentioned that's one of the things that you can do with the outlier analysis. A lot of people talk about, I've seen this number around 60% of the cost of an AI project is related to data cleaning. And I've actually talked to some people who say that that's an underestimate. I've heard people say they think it's more like, in their experience, it's more like 80% or higher. I mean, anyone who has done, some AI projects, I know some of you guys have based on the earlier polling results, you'll understand how important it is to have good, clean data. If you put in poorly clean data, your AI algorithms are not going to be able to produce anything really useful at the tail end. So identifying things that shouldn't be in the data and getting them out is pretty important. So I want to talk a little more about a couple of the different categories of cleansing that outlier analysis can handle. So I mentioned that first category of outliers before. And part of that was what I call data errors. So just to talk a little bit more about these. So these are cases where, for instance, you may just not have any data at all reported for a certain period of time. Or you might have failed calculations or invalid values. I've seen failed calculations result. I've seen cases where, for instance, the failure is a division by zero or an almost division by zero. So all of a sudden, values that are normally in the range of 0 to 100, all of a sudden you'll get millions or billions or higher recorded in these things. So you can get some pretty weird results. Now, the good thing about these are they're usually possible to automatically filter them out. It can be, it's not too difficult to write some code that can just detect these and filter them out. Or the algorithms that we work with, for instance, will generally detect the vast majority of these kinds of problems automatically and will remove them from your data set. So these are a bit of a less of a concern. If your system doesn't do it automatically, it's usually not hard to extend it to deal with it. The ones that are a little more challenging are what I think of as semantic errors. So these are things where there is data present, but the data is nonsensical. So for someone who understands the data, they can look at it and say, well, that's just not possible. I mean, an example might be, let's say you're measuring temperatures and you have something that is always above 0 Celsius. That's always, there's always liquid water involved. And all of a sudden you see a value of minus 20 Celsius. A subject matter expert, algorithmically, there's not really any way to look at that and say, well, those values are obviously wrong. But someone who understands the domain can look at that right away and say, that doesn't make any sense. Or, you've got something with liquid water and all of a sudden it's jumped up to 500 degrees Celsius. Well, there's no way that could happen. So you can identify the values that are really just kind of nonsensical. Another challenge that we've seen, and I'll actually talk a little bit about a real world example of that in just a minute, are interpolated values. So some IoT systems will actually, if there's missing data, instead of just leaving it blank, like I talked about here, they'll helpfully linearly interpolate the data for you. And if you're missing, 1 timestamp or 2 timestamps, that's usually fine. But if you're missing a lot of data, you're going to get some potentially really weird values in the middle, and so that can also result in pretty major problems. And then finally, I think I mentioned this before, maintenance periods or plant shutdowns. Or I live in Quebec, and we just finished the previous 2 weeks to this one were what they call the construction holiday. So virtually every construction worker in Quebec was on vacation for the last 2 weeks of July. So if you're looking at data that deals with anything related to the construction industry in Quebec, you're going to see very strange results. And again, they aren't necessarily going to be out of whack enough that they could be automatically detected, but the results are going to be very weird. Now, the good thing is that almost all of these kinds of problems will be strange enough that they will actually show up as outliers in an outlier analysis. And that's one of the big values of using outlier analysis. In addition to finding things that are anomalies, they're also going to find these kinds of semantic errors and make it much easier to identify them so that they can be cleaned out of your data before you do the analysis. And to just give a concrete example of that, a while ago, we were looking at some real world IoT data. It was about 12 months worth of data. And when we ran the outlier analysis on this, we found 90% of the outliers happened in a single day. In fact, less than a day. It was within a single 12-hour period of a day. And we were pretty confused. It didn't make any sense that we were seeing, like, out of 12 months, almost all of the outliers were happening in this tiny short period of time. We actually, for a while, thought it was a bug in our outlier analysis engine, actually. So we went and talked with a subject matter expert, and what they were able to tell us was that there had been missing data for one particular attribute for a 12-hour period on that day. And for that 12-hour period, at the beginning of the period, the attribute had a really high value, and at the end of it, it had a really low value. And so the IoT system helpfully just did a straight linear interpolation over those 12 hours between those two things. And this particular attribute tended to be, all on or all off. So it didn't spend a lot of time in between these two values normally. It was usually just at the top or the bottom. And so having a 12-hour period where it was kind of in between that minimum and maximum value resulted in all kinds of weirdness that basically made our outlier analysis tool think that everything in that period was an outlier. So once we recognized that, we were able to basically eliminate that period of time for that attribute from our analysis. And then all of a sudden, we got much more reasonable results. We saw the results spread out over the entire 12-month period, and we actually found much more interesting outliers detected over that entire period. So, and this again, we were relatively lucky in that there was only one really big case like this here. But in practice, you may have to go through that process multiple times. You may find that the first, many times you do this kind of analysis, a reasonable number of the results you're getting are actually not leading to anomalies, but are leading to kind of semantic errors that you need to filter out to kind of get to the underlying gold, I guess, of the actual useful anomalies that you can start to take action upon. Okay, and with that, let's do our third and final poll.
Attendees, please let us know, what is the biggest challenge you see in terms of using industrial AI at your company? Is it management/company culture doesn't see value in AI? Or hardware/machinery of interest is not instrumented to collect data? Or data quality/data organization is too poor to work with? Or lack of data science/AI experience? We'll give you a few more seconds to submit. So our clear winner here sits at 38% of lack of data science/AI experience. And at 29%, we have hardware or machinery of interest is not instrumented to collect data. Thank you, attendees. And back to you, Warren.
Okay, thanks, Maria. Yeah, and again, that actually matches, again, my experience pretty well. I think that we see some places that don't recognize the value of AI, but most companies these days are starting to see the value of it. And the challenge is more the execution. And so it's either getting the data, or if you're getting the data, figuring out what to do with it. So that's definitely that makes sense. And I'll talk a little more, but the application we've been working on is actually well suited to help in that sense. We try to help people get by with less formal data science or AI experience. But anyways, let's continue and talk a little more about this. So I want to talk a bit more. I talked at the beginning a little bit about univariate versus multivariate detection. And so I want to talk a little more about that here. So as I said, low dimensional or univariate outlier detection looks at a single attribute or a few attributes at a time, and looks for kind of extreme values and unusual patterns. Now, there are advantages to this, and in cases where it works, it's actually fantastic. It's quite easy to understand the results you get back. And it's relatively easy to implement, even if you need to implement it yourself. But the problem is that when you're dealing with especially industrial data, it's not capable of identifying a lot of the kind of real world problems. It might tell you, oh, the temperature was high here, but it won't tell you, why the temperature was high or why there was a problem this time when the temperature was high, but there wasn't a problem last time the temperature was high. And so it's a lot harder to get data out of it that you can, I guess I would say it's a lot harder to get kind of real useful insight into your data from something like this. So you aren't going to be able to use it to do root cause analysis. You aren't going to be able to use it to do process improvements, things like that. So at least not without a lot more work. It takes a lot more investigation to try to figure out what's really going on behind the scenes. So now multivariate outlier detection addresses some of these problems, but of course introduces a few more of its own. So multivariate, when I'm talking about high dimensional or multivariate analysis, I'm talking about taking a lot of data, I tried to show what it might look like if you had a single graph showing all of these things. And even this is pretty small. You're often talking about hundreds of attributes at the same time, or even thousands. And then you want to look through all of that data and find times where something unusual is happening. Now, the good thing is that this is much more applicable in an industrial use case because, as I said, it's very common in industrial scenarios to have large amounts of data that you need to kind of look for challenges in. It's a lot more complicated to do right, but it definitely has the potential to provide a lot more value in terms of gaining real insight into your data. But it does have a problem. It can be very, very hard to once you identify that point, it can still be hard to get to understanding of what's going on behind the scenes because you do not have necessarily a good grasp of what's changing. Unfortunately, a lot of high dimensional outlier algorithms out there will identify the time when the problem occurs, but that's it. They won't give you any additional information about what's going on. And so if someone says, well, there's an outlier at this particular time, and you've got even 100 attributes to look at, it can be exceedingly difficult to try to figure out what the heck is going on. So one of the things that we've been working on for a while now is producing an explainable multivariate outlier detection tool. So one of the things that we can do is we can take hundreds or thousands of attributes and across a really long period of time. And we not only identify when the time at which the outlier occurs, but we can also tell you which of the attributes of that full set, we can identify a small number of them, which are what we call the influential attributes. So these are the ones that are kind of most relevant in terms of making these points an outlier. So that makes it much, much easier, even when you have hundreds or thousands of attributes. You can still actually get some pretty powerful insight into what's going on in your data by looking at this kind of thing. So analyzing by looking at the behavior of these influential attributes and looking at where they are in terms of the global ranges of the data, you can actually make some pretty powerful statements about where these outliers are and what's causing them. And when you're working with a subject matter expert who really understands the domain, this starts to turn into actionable stuff very quickly. It becomes much easier to really understand what's going on and potentially what can be done to either replicate it if it's something you want replicated, or stop it from happening in the future if it's something you want to stop from happening in the future. So fundamentally, what we're trying to do is move from a world where you're taking all of this data and you have a data scientist or an AI expert who spends huge amounts of time digging through all of this data, cleaning it, trying to develop some insights out of it before you can do anything useful with it. We're trying to build an app that lets a subject matter expert do the bulk of the work with, sometimes they may need a little bit of help from a data scientist, but the goal is to, by and large, let a subject matter expert work with the data on their own and be able to develop, some very deep insights, let them do data cleansing, let them see what's going on in the data and assign labels to stuff that's going on in the data. So that they can assign labels to it, and then they can use those labels for both sort of some of the business analysis stuff that we were talking about. So, trying to avoid problems, trying to understand what happened, the root cause of various problems, or trying to institute, process changes to either encourage the things you want to have happen or stop the things you don't want to have happen, setting up, notifications and things like that based on the data that's found. Or then feeding that clean labeled data into other AI algorithms, which can then help with things like predictive maintenance or demand forecasting or a variety of other AI related tasks. So that's kind of what we've been trying to accomplish. And I want to spend a few minutes showing you now a demo of the application. And I'm going to be very brave today, and I'm actually trying out a live demo. So hopefully everything will run smoothly. So when you are first trying to do an outlier analysis, the first step is to define what we call a scenario. So that's basically the period of time you want to look at, how often you want to look at the data. You define where the data should come from. In this case, we're pulling data out of an OSI soft Pi server system. You then need to define kind of what assets and attributes you want to look at. So we provide a mechanism to reach into the Pi system and pull out all of the types of assets that they have. They're called element templates in Pi parlance for any of you people who work with Pi. So you can get this list of all these different asset types. In this case, we're going to look at computer room air conditioning units. Once you select the element type, we fetch all of the different instances of that element type and all of the attributes associated with that element type. So these are all of the physical pieces of equipment or whatever that match this element type that throughout your environment. And then these are all of the sensors, the information that's being collected about these particular attributes. And so depending on what you're trying to do, sometimes it makes sense to look at everything, but in most cases, you're going to want to look at one particular aspect of these machines. So you may want to pick a particular set of attributes that are related to whatever aspect you're trying to look at. I mean, this is possibly one of the areas where in some cases you might need a little bit of help from a data scientist to kind of establish what might be good scenarios to set up. But once you've set up good sets of attributes, you can actually save out templates of useful sets of attributes for particular element types. And so it becomes easy to recreate them on different sets of assets or over different time periods if you need to. So once you've kind of selected the assets and the attributes you want to work on, you can then run the scenario, which involves basically reaching into the underlying data source, pulling out all of that data, and then doing the outlier analysis on it. What we do, so it takes a few minutes to run, so I'm not actually going to do the actual analysis live. But once we've done that, we basically take all of the outliers and we apply a clustering algorithm to them. So in this case, we've found about 300 and some outliers, and we've grouped those together into 32 clusters. And we can now go and look over here, and we can look at all of the clusters that were found. And for each one, we tell you, how many outliers were found, what attributes were associated with it, what the time period was for the cluster. And you can pick a cluster that looks interesting, and then we'll show you a summary of that cluster. So in this case, we're looking at this particular cluster on ambient humidity being the primary thing. This is, by the way, this particular data set is a synthetic data set that we came up with that is very good for kind of showing off the capabilities of the application, but not necessarily the most interesting in terms of actual underlying data. I will show you briefly a real world data set after this, but this is good for kind of showing off some of the capabilities. So here we've got a cluster of 8 outliers. Here we show you some general information about the cluster, and we identify a typical point, which is kind of intended to be a representative point of all of the points in the cluster that you can use to start trying to understand what the meaning is behind the cluster. Over here, we show you the influential attributes for this point. And so here you can see that 90% or 96% almost of the influence comes from one attribute, the ambient humidity. And then the next one down is the cooling power, and then it kind of drops off beyond that and gets quite low very quickly. This panel up here at the top shows you a scatter plot of all of the outliers by the top two influential attributes. So you can see kind of a projection of all of the outliers into those two variables. So you can see what the shape looks like of the thing. And so here you can see that all of these are have an ambient humidity, or almost all of them. There's one guide here that's on the other side, but almost all of them have a low ambient humidity of under 15. Here we show a breakdown over time of all the outliers. So you can get an idea of what the relationship is between the outliers over time. And so here we can see it runs from November 25th to December 3rd, and they're kind of relatively evenly distributed. Maybe it's speeding up a little bit towards this end, but they're relatively evenly distributed throughout that time frame. And then the panel here at the bottom shows you contextual information about the outlier. So on the right here, this is what's called a box plot, and it shows you kind of where the bulk of the data is, both globally in orange and for this particular cluster in blue. So you can see that globally, the range is, I don't know, maybe 21 to 23, something like that. Whereas in this cluster, almost all of the data is under 15. Which will usually, that will be very useful for a subject matter expert to try and understand, what the meaning is of this particular thing. And then the center panel here actually shows you the green line at the center is the instant where we detected the outlier. And then we're showing you contextual information 20 minutes before and 20 minutes after for the behavior of this particular attribute. And so that'll give you some idea of what's going on around the time that we identified the outlier. So in this particular case, you can see that it is indeed running along between maybe 21 and 22, and then it jumps down to almost zero. Well, actually, sorry, not almost zero, to 14 at the, or 14 and a half at the 0 point, at the instant that the outlier was detected. Now, if you want to care, so the usual approach is that people then want to figure out if the rest of the points in this cluster really are representing the same kind of thing. And there's a couple of ways that you can do that. You can go through point by point and look at each of the outliers. And then what we will show you is kind of where you are, where both of the points are in the scatter plot. We actually now show you the influence for both of the 2 points, the typical point and the current point you're looking at. And down here, we overlay the contextual graphs for the 2 points. So the blue is the typical point that we were looking at initially, and the orange is the typical point, is the curve for the point that we're looking at now. So that gives you an idea of whether they really do represent the same thing. Now, if you have a lot of them, it can be kind of painful to go through one by one. So we do have a mechanism where you can go up here and you can select a group of things that you think are all related in the scatter plot, and we'll actually build a 3D display of all of those points. So now, each of these lines here is effectively the same as that graph I was showing on the previous thing, but split into 3D. So the vertical axis is the ambient humidity. This axis here is time, with 0 being the instant where the outlier was detected for all of the points. And then we're showing the outliers here. Now you can see, though, that the graph looks very different, and there's this one point that has a value of 1.1 billion. So this would be one of those data errors that I was talking about. This is a ridiculously large value. Obviously, the humidity could never get to that point. And so we can go over here and we can turn off that particular one and remove it from the display. And now you can see the remaining points all look more or less the same. They aren't identical. Looks like the pink one here, we might have gotten 2 dips side by side, but they're pretty close. So if you think they're all the same, you can actually go in here and directly apply labels to all of the points here. So I can say, I'm going to call these all low humidity, for instance. And now all of the remaining points, not the purple one that I turned off, but the remaining points have all had that label assigned. Now, if you had hundreds of them, we actually show them to you in groups of 20, because it becomes a little hard to read a view like this when there's too many points. But it becomes pretty quick to scan through points and quickly turn off any that look different and label the ones that are there. And it's a pretty easy way to label a lot of points very, very quickly. Now, once you're done there, you can see in this view, you can see the scatter point, or the scatter plot is now showing the low humidity points that we labeled. So they're all easy to see which ones you actually have labeled and which ones you haven't when you're done here. Now, across all of the scenarios that you work on, we gather together all of the labeled data into a separate labeling UI. And so you can see, I mean, here I've only got the data from this one scenario, but if you'd run multiple scenarios and gone through and labeled all of them, all of them would be grouped together here. So you can go and see, for each of the labels that you've created, you can see all of the labeled outliers and what scenarios they came from. You can go into each scenario and look at which points were labeled, get some information about them, relabel them if necessary, if you end up determining later that one of these points isn't a low humidity case or whatever. And then you can also export all of it. So you can basically bring all of that data out into other applications to do additional analysis or data on them, data analysis on them. We also bring together the data errors that I mentioned. So semantic errors would have to be handled through labels. The application itself can't detect the semantic errors, but if there's data errors in this that are encountered, we do actually flag those separately. And so you can go to the separate UI here and see what data errors we detected, which in this case, there are some that are over 9 standard deviations from the mean, so way out of whack. So that 1.3 billion would have been like this. So that point would not have actually been detected as an outlier, but I think it happened to be happening near a point that was detected as an outlier, which is why we ended up seeing it in the graph above. So you can get information here about any of the data errors that were found in case you need that to deal with with what you're working on. Okay, so as I said, this is a kind of a synthetic data set. Let's take a quick look at a more realistic data set. So this is data from a water processing plant that made publicly available about, I think it was about 9 months of data over which they had 7 plant shutdowns, basically. And so they were looking for advice on how to improve that. So we ran their data set through. We found about 500 outliers over the course of the 9 months, and that are clustered together into 53 clusters. I'm going to jump specifically to a cluster that is relatively interesting because it's happening just before one of the failures. So yeah, you can see this cluster here is happening on June 28th, and the endpoint is 9/31. There's a failure just before 10 p.m. On the 28th. So this cluster is happening basically just before one of the failure points. So if we go and look at this cluster, you see a few things here that are different from the kind of the synthetic data we were looking at before. So you can see the outlier influence is much more interesting, basically. So these outliers, instead of just a single influencer like we looked at before, there's actually a quite a number of highly influential attributes associated with the point. Another thing you'll find is that we have grouped together some of the outliers. So before there was a single green line here showing where this particular outlier took place. Now you're seeing a period of about 4 minutes, I guess 5 minutes actually, grouped together. And it's because there were a number of outliers that all happened in tight sequence, basically 1 minute apart. And so instead of handling them separately, we group them together into a single event, so it's easier to kind of understand what's going on. And so you can see the time period that they happen over in each thing, and you can see we show the same thing here. So we actually show the duration of each event on this view. So you can see each of them actually has more than each time this happened. It was actually stretched out over at least a few minutes, and the occurrence just before the shutdown is actually the longest of the occurrences, which is kind of interesting. And now instead of a single attribute graph, we're actually showing you graphs for a number of the more influential attributes here. And what you can see here that's interesting is, again, using the box plot that I showed you before, you can see that, for this attribute, for instance, the normal range is over 600. But all of the points in this cluster are right around 200. Same thing here. It's normally about 2.5, and we're close to 0. So each of these attributes, we're seeing values that are way below the normal range. except for the final one, which you can see is going up to a peak right around the time that we've flagged these outliers. And you can see these points are actually way higher than usual. So it's the normal range is up to maybe 500. And here, though, you can see, in fact, here it's like 1,200 up to almost 1,500, basically. So actually over 1,500. So at that, it's absolute peak. So you can see the range that we're getting inside this cluster is way higher than before. So for a subject matter expert, I mean, I don't know much about water plants, so I can't comment too much on the actual meaning behind this. But this is the kind of thing that a subject matter expert can look at and can identify what action should be taken. At a bare minimum, looking at these ranges allows you to create notification models where, okay, well, if we see these 4 attributes or 5 attributes really low and this attribute really high, above 1,200 or something, that can be added into a notification management system so that you can flag that happening. And in this particular case, you would have gotten a warning roughly potentially as much as 2 hours before the plant shutdown, so that you could actually take action on that and potentially avoid or at least reduce the difficulties caused by that particular problem. Okay, so that's the extent of the demo. And so, I mean, I hope that was useful. My goal was to give you an understanding of how you could, what outliers and anomalies are and how you could use them to help with industrial IoT and AI. So I hope I've managed to achieve that. And so we'll close the presentation and move to questions now.
Thanks so much, Warren. We have a few questions coming in. Our first question comes from Mohammed. How do you handle outliers or anomalies in a process that is influenced by operator interaction and decisions?
That's a good question. There could be a few ways of doing it. You could actually, if you're looking at like historical analysis, you could actually make sure that the operator interactions are actually recorded in the IoT system. And so then you can actually, try to correlate when particular actions were taken, or potentially what, fundamentally if the operator is changing certain settings, for instance, you would want to make sure that those settings were also being tracked in your IoT system, not just the sensor outputs. That way, when you're looking at the analysis, you'll actually see both the results, but also the changes of settings that are being made, and then both of those will be factored into the outlier analysis, and you'll be able to see that when these particular settings were in place, perhaps when these settings were made, when a particular temperature value was high, then something happened. So that would help you to incorporate that into the results.
Thank you. Next question comes from Chan. How do you assure the security of the data?
That's also a good question. It depends a lot on, so in our case, I mean, we're pulling the data onto our local server and working on it locally, so we can keep the data quite secure. If you're collecting the IoT data across a large number of physical sites, for instance, then you do need to be pretty careful about how you are actually pulling that data together. The best advice I can give you there, I'm not really an IoT expert, but there are a lot of very good quality IoT data historian systems out there. As I said before, we work with OSI SoftPi, and there are a number of others like that. And their bread and butter is making sure that data is kept reliably and secure. If you want to move into the cloud, there are roughly equivalent at least systems that both AWS and Azure provide, where they will also provide a good deal of security around the IoT data. You will have to make sure that encrypted channels are used between your site and the cloud systems if you're doing that. But yeah, I think those are the key things to keep in mind in terms of security.
Awesome, thank you. Next question comes from Ahmed. How is the connected plant, I'm sorry, hang on. How the connected plant is more productive? Also, how do we bring assets online and start harnessing the value of the IoT?
Okay, well, let's do two parts. Let's see. So in terms of the benefits you get from a connected plant, I think it's a lot of the stuff we've just been talking about. I mean, if you aren't connected, if you aren't collecting data from all of the facilities in your like the machinery in your plant, then none of the things that I've talked about today can be done. The first step is to have all of your machines instrumented, have some kind of a system that can pull all of that data together and map it to the various assets and those kinds of things. So that's, I mean, there's lots of other benefits you can get from a connected plant as well. Like there's a lot of people, you can look at all of the various benefits people talk about in terms of, maintaining digital twin environments and so forth, which go far beyond some of the outlier analysis and AI we're talking about today. But so yeah, there's a lot of benefits to a connected plant. In terms of how you get there, that can be challenging. If you're dealing with new hardware, most new hardware will already have pretty powerful instrumentation built into it. But if it's a brownfield, if it's a, an older facility with older hardware, there are lots of, I mean, this isn't really something that we do, but there are a lot of companies that will go in and help you instrument existing hardware. So they will add sensors to it. They will add, all of the mechanisms and the hardware necessary to collect the data from those sensors all into a centralized location and push all of that data into a data historian so that you can start to gain some of the benefits of having all of these things connected and instrumented. I hope that answers the question.
Thank you. Next question comes from Nikolai. Can you explain the difference between cluster and global sets?
I'm not 100% sure what you mean by global sets. We tend to use the word cluster to simply mean a group of things that we believe are related. Now that's a pretty broad statement. There are a lot of different clustering algorithms that will try to identify what what kind of a cluster you're dealing with or how best to cluster your data. There's some of the standard ones are things like k-means and DB scanning and DB scan and so forth. And so there are a lot of different algorithms that will take a bunch of points and try to identify clusters for them. But I'm actually not familiar with the term global set, so I'm not sure how I can contrast the two. So sorry, we can look into that more and maybe get back to you with a more detailed answer.
Awesome, thank you. Actually, Nikolai just followed up. He says, in the live demo bottom graph, Legend showed cluster and global.
Oh, okay. Sorry, I didn't understand what you were speaking of. Yeah. Sorry. Let me. I can actually go back to the app for that. So you're talking about down here. So here, what this means is, we're looking at, in this case, this is the water plant example I talked about. So we're looking at 8 months of observations. So over the entire 8 months, this particular attribute, the flow value for pump 1, was mostly between 600 or just over 600. I think this is cubic feet per minute. So this is kind of the global range of this particular attribute. The blue dot here, you can see how tightly clustered it is. It's just showing up as a single dot, is the range in this cluster. So in this cluster, it's hovering right around 200 for every point in the cluster. In fact, you can see up here that it ranges from 200.5 to 200, just over 202. So it's pretty tightly grouped around 200 in the just over 200. So it's the difference between just this set of outliers that we've gathered together versus the value over the entire range of data. So hopefully that answers the question.
Thank you. Next question comes from Angel. When interpolation is done, can one attempt do something different than linear interpolation or some type of non-linear interpolation?
That's very dependent on the IoT system, and it depends on some of the systems that I've seen. They tend to default to linear interpolation, but I think they do have ways to, if you know, for instance, that other distributions will better match your data, I think you can enable other ones. But it's very, our system itself relies on the underlying IoT data management system for that. But I think most of the ones that I've worked with anyways do provide ways to do something slightly more sophisticated. I mean, the problem again is if it's 5 minutes of data, then something more sophisticated than linear might do a little better. But if you go for a long period of time without data, then there's not really too much you can do. There's only so far you can go with any kind of prediction. I mean, unless you're trying to frankly, even if you're trying to do something much more sophisticated, you're gonna, after the course of like an hour or something, you're just basically gonna be guessing. So, but yeah, I hope that answers the question.
Thank you. Next question comes from Vinod. In the software, how can we determine the predictive maintenance schedules?
That's a good question. So the software that we're providing right now isn't directly usable for predictive maintenance. We're actually looking at doing some extensions to it to kind of more directly enable that. But what it can help you do is to identify things that that could feed into predictive maintenance environments. So, like I said, in this particular case, if you've identified that the only case where this particular combination of values happens is just before one of these shutdowns, then and your subject matter expert agrees that this is a bad combination of things, then this is the kind of thing that could potentially be used as a trigger for, in this case, it would probably need to be an emergency operation since it's like only a couple of hours before the failure. But more broadly, you will identify things like this that may be found days or weeks or months before a problem occurs. But at the moment, we're just kind of identifying things that could be fed into a predictive maintenance system. We aren't actually doing the full predictive maintenance ourselves. Although, as I said, that's tune back next year. We may have more to show. But for the moment, this is more material that can be used to feed into a predictive maintenance, a separate predictive maintenance tool.
Thank you. The next question comes from Partha Sarathi. If we handle a data, for example, we are getting 10,000 entries, and if the outliers started showing up from the last data entries, how do we manage this? Like if the outliers are appearing in the last entries of data from 9,000 or 9,500?
Just not 100% sure I understand. So I think the question is that you're getting a large number of data points and you're only seeing outliers at the very tail end of the analysis.
Yes.
So yeah, I think that's where it would depend very much on the particular types of analysis you're finding. That probably could potentially mean that something is starting to fail, and by looking at the particular pattern of what attributes are contributing to those outliers, a subject matter expert hopefully will be able to figure out what the underlying problem is. And again, it's a without actually looking at the data, it's a little hard to say, but you could imagine that it's something like this where a particular pattern of something showing up that's much higher than usual suddenly starts to happen right near the end of the data set. That could well mean that a bearing is failing in a pump or something is starting to go wrong that is going to lead to a more serious failure afterwards. But I think you'd need to look at the specific types of outliers that are being found with the subject matter expert to figure out what's really going on behind the scenes.
Thank you. Another question from Angel. To determine the clusters, is a formal cluster analysis performed, or are the clusters determined visually?
Right now we're doing a kind of a combination of different, we've experimented with a bunch of clustering algorithms. We've used k-means, we've used dbScan. Right now we're using a combination of looking at the types of influencers and the values of the influencers to try to group together the items that have similar sets of influencers, which we found tends to correspond to being the same event. So we're still fine-tuning the algorithm, in all honesty. What we have now works reasonably well, but isn't perfect. Most likely, we think we're going to end up with something that's kind of a combination of the current approach and possibly incorporating some aspect of more traditional clustering algorithms like k-means or dbScan. Well, we aren't doing it visually though. No, you know, an unattended analysis of the data to identify what objects or what outliers should be grouped together into each cluster.
Awesome, thank you. So we only have time for one more question. This one comes from Ardash. How is this outlier analysis applied in the field of mechatronics engineering?
Um, we haven't looked too much yet at mechatronics. I assume he was talking about mechanical and electrical, I guess, I think is probably what he's talking about there, electronic stuff. We haven't really looked at that too much, but I could definitely see it being useful in looking at, for instance, potentially heat distribution. You could look at thermal information inside a case, for instance, to try to determine, you know, what potentially looking at you know, both mechanical and control points. So like, you know, for instance, if there are computer elements in there, looking at how much current is going into the CPU and how much current is going into various other components versus looking at temperature related data to try to identify anomalies in the temperature readings within it. Maybe I will admit I'm not an expert on mechatronics, so we could absolutely follow up with you. We do have people at Maya who know 100 times as much about that space as I do. So we can follow up with you and maybe get some more concrete answers for you there.
Awesome. Well, that's all the time we have for now. Thanks so much, Warren, for providing us with great content and value today. And thank you attendees for joining us. We hope you'll return for future webinars. Bye for now.